Awesome. The mic works. Good morning. It's so wonderful to see literally everybody in person. It's a close call. And so in this session, we're going to talk about building Game Boy emulators and, well, secretly the history of computing, and also secretly about failure and a whole bunch of other stuff. It's going to be a bit of a wild ride. So let me tell you about myself a little bit. So I'm David, and I'm an independent software consultant based in London in the UK. Now, I work for myself, which is wonderful. I would recommend it to everybody. Being your own boss is the best. So I mostly mentor developers, and I do kind of strategic work for UK dot-coms. So I've had a wide range of really, really pretentious and pointless job titles. Head of engineering, chief technical architect, principal engineer, blah, 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 which all sounds a lot fancier than it really, really is, I swear. Really, I just love making things. That's the thing I really enjoy doing, and I love the people that make things, and I try and spend my time helping them do that. I've written a couple of kids' books on programming and JavaScript, Get Coding 2 and 1, available in all your regional languages. And recently, I made a Game Boy emulator. So before we dive into any of that, I want to talk about what emulation really is. Emulation, it's very, very technical, is the practice specifically of writing software on one system so that it can simulate the runtime environment of another with the goal of running software for a different piece of hardware or environment. You've probably come across this before, right? And there are a couple of different broad approaches to emulation. Now, there's low-level emulation, and what that is where you implement the behavior of the raw hardware, and then the software designed for it should just kind of work. And then we have high-level emulation, where you attempt to run software natively on your target platform, and you intercept the system calls of the original piece of software and re-implement them in something more native. Now, most game emulators actually are a mix and match of those two things. Often what they do is they emulate low-level hardware architecture while re-implementing high-level things. Stuff like 3D drawing calls are a great example of where they can shortcut and be really performant. They do that in modern APIs. So there are loads of really famous emulators, from kind of games console emulators to operating system emulators to hardware emulators. So if you've ever run any kind of VM, you run an emulator, right? So when I say I built a Game Boy emulator, what I'm really saying specifically is I built a program that can run Game Boy software while the Game Boy software itself believes it's running on Game Boy hardware, which is a bit of a mouthful, but it's important we're precise about these things. So why would you ever do that? It's all a bit pointless, really, honestly. But that's the fun of experimentation. That is the point. There's lots of different answers to this question. But firstly, I really just wanted to see if I could do it. Simple as that. And so often, we are forced to live in this kind of brutalistic corporate hellscape where only things that have to exist for money ever get rendered into reality, right? So this is literally the opposite of that thing. Game Boy emulators totally exist. Like, if you want to play Game Boy games on your computer, I'm going to open up now with please don't use my emulator. Don't do it. Please don't do it. It's incomplete. It's possibly buggy, and I'm not going to help you wake the windfish in Link's Awakening. But this story is actually a little bit different, and it actually starts in the 70s, before I was born, thank you. And it starts with Pong, and it starts with an interpreted language called Chip 8. So we're going to use it to understand what emulation really is before we talk about Game Boys and Super Mario. Sounds delicious, right? So I'd started toying around with emulators as part of what I suppose now is this decade-long experiment in running coding dojos. So I do a lot of training for teams, and especially web dev teams, looking to upskill or pick up things like TDD. Now, while I was looking for different puzzles to set people in dojos, I'd plundered the archives of the old website Ruby Quiz, and it's still online, and it's still actually excellent if you're looking for kind of katas to do to get better at random stuff. So they used to run weekly programming puzzles, and I ended up running the Chip 8 kata from there quite a few times. It's Ruby Quiz 88, if anyone's curious. So the Chip 8 kata provides a binary program written in Chip 8, which is a machine language, and it tasks you with writing an interpreter for it along with outlining the hardware that the program runs on. Now, chip 8 has 32 opcodes in total. But the program supplied by the quiz only uses like a small subset of them to make it a little bit more approachable if you've never thought of doing emulation before. I remember thinking it sounded absolutely terrifying the first time I read it. It's like, you want me to write a decompiler and a... what? Yeah, so that was, I think, everybody's response when they see it. So, okay, firstly, like opcodes, machine languages, what? So let's look at a quick example of how computers, and specifically our computer processors, our CPUs, work, before we go any further. So when processors are manufactured, and you'll have heard all these words before, being technical people, but it's, again, understanding what they really mean is very specific, especially if you don't have a computer science background. They're manufactured, and they implement a specific instruction set. Now, this instruction set is literally just the list of things that a processor can do. Now, anyone old enough to, might remember the 1990s competition between CISC and RISC architectures, which stood for complex instruction set and reduced instruction set computing, respectively. Now, these CPU instructions were what they were using when they said complex or reduced. That's what they were referring to. Now, the instructions themselves are built into physical hardware, and they can be programmed using machine code. Now, every processor, well, family of processors really, has its own instruction set. And as a result, it has its own machine code. So when people say things like they're programming in assembly, they're normally referring to a specific kind of assembly for a specific piece of architecture. So machine code itself is a strictly numerical representation of all the operations that a processor can perform. Now, an opcode, shortened from operation code, is the part of the machine code that specifies what a CPU should do. Mouthful again. So the assembly language for a given processor can then be assembled, hence the name, into machine code, and is a low-level abstraction over the instruction set of your processor. Now, when we talk about assembly languages, what we really mean, again, is programs written for a specific CPU's instruction set. So then the processor in hardware implements those operations. It implements things like adding two numbers or placing a number in memory at a specific location. Now, the opcode, when a CPU is running a program, tells the CPU which instruction to execute when it encounters it. So I appreciate this all sounds really, really abstract. So let's look at this example and we'll kind of try and understand it. So on the left, you can see the raw machine code of a chip 8 program that we're going to come back to a few times. And that same machine code then decompiled into its corresponding instructions on the right. Now, besides the opcode itself, most instructions also specify the data they're going to process in the form of what they call operands. Now, honestly, you can just think of them as the parameters that are passed to the opcode. It's really, really simple. And normally these parameters are just a memory address or a register address. A register is just some memory that's on the CPU itself. Now, a memory address is just a number, normally expressed in hexadecimal when you see it written down, and they're just a number starting at 0 and counting up to however much memory you have. Now, when people talk about how many bits a CPU is, what they're really referring to is the largest number that the computer can hold in memory when expressed in hexadecimal. So literally, the more bits, the larger the total amount of memory a CPU can address. So we're starting to build this picture of how hardware works on the lowest possible level. Now, a CPU that only understands 8-bit numbers, like, say, the Game Boy, can only understand the numbers 0 to 255 as memory addresses. Therefore, it can address 256 memory locations. Subsequently, a 16-bit processor can understand the numbers 0 to 65,535. Therefore, it can address 65,536 address locations. Now, literally, the bigger the number, the more memory you got. Now, each memory location can then store any amount of data, depending on the implementation. In the case of chip 8, each memory address stores 8 bytes of data, and the chip 8 hardware has 4,096 memory locations itself. So this is the foundation of all computing. I can give you a computer science third year degree now. I think this is basically it. This is what you went to university for. When you use a higher level programming language like C# or JavaScript, the runtimes that execute those programs have been compiled down for your specific CPU architecture. This means that ultimately, somewhere, something has been translated down to machine code and is executing on your CPU. And whenever you create variables in your programs, somewhere, something is putting things in memory registers for you. Now, it's all buried under loads and loads of abstraction, and most memory manipulation is done by interacting with the operating system, and the operating system decides what lives where in memory, and this process kind of happens transparently for every single line of code you ever write. So, after our crash course in like how computers work, let's take a look at a Chip 8 program again, and how some of its opcodes actually function. Now, the program in the top left portion of this slide is the original RubyQuiz Chip 8 test program. It's just a raw binary file in the machine language of the Chip 8 computer. Now, when you open it in a hex editor, that's literally a screenshot of what it looks like. I think that was VS Code. So to interpret this program, what you do is you loop through each of the bytes, and if you take a look at the snippet of C# that I've thrown in the slide as well there, we're just loading this file as a byte array and like printing it out on the screen. So in C#, the bytes are all represented in base 10, so as integers. And when you look really carefully, you notice how the first number gets printed as the number 97, which is 0x61 in hexadecimal. Now, if you look at the first two digits of the original program at the top, this is the same 61 from the very start of our test program. So you can see how we can chunk through these bytes. So our documentation shows that our Chip 8 interpreter operates on 2-byte operands. So to run this program, you need to loop through each pair of bytes in the binary blob, in this case reading the 61 and the 77 together, and then you process them according to whatever the hardware behavior is meant to be for that opcode. So if we zoom really, really in on that first 2 bytes in our file, we've got 2 hex numbers, 6177, that make up the opcode and then its operand. Now this is expressed in the documentation as 6xkk. Now this is explained in the quiz as an opcode that sets memory location x to the constant value kk. So 6177. Now if kk is an 8-bit constant, literally the hexadecimal value 77, or 119 to humans, our first opcode says 6, do something, a constant, 1, the memory address 1, and 77, the decimal number 119, which translates to put 77 into memory location 1. So if you imagine memory locations like a big array or like an Excel spreadsheet or something, you can interpret the entire Chip 8 program by implementing each one of those opcodes and writing code to perform the logic, with different opcodes, like 6 in this case, doing different things. You know, it's a switch statement. Now, it's a really scary looking problem, like really, really, really terrifying, but it's not really very complicated when you break it down into its really, really small pieces, just a switch statement. So the cool thing about this is because it's so far out from what people normally find themselves working on. You know, people attending these dojos always found it exciting when they made progress, because when you take someone whose job is getting a number from a database and putting it on a web page, that's me, that's basically all the work I ever do, and then show them that the same skills that they have that lets them do that in a nice way is the same thing they can do really, really cool things with, they get really excited, right? It's fun. So I ended up running this dojo a lot with plenty of different audiences, and I think there's nothing more fun than doing this, right? Showing them showing people how capable they are with a bit of lateral thinking, and that programming doesn't have to be like a blunt commercial-only thing that we just do to get paid. It can be fun, enjoyable, intellectually challenging. The end. No. So. Now you know how to write an emulator. End of demo, right? Now let's talk about Game Boys. So Chip 8 is a useful introduction to this kind of low-level programming because there are only 32 opcodes in total. And the RubyQuiz Kata, I think, uses 10 of them. So give it a crack. Like, honestly, it's great. I think it's important to remember literally anyone can do things like this. And I'm not a particularly incredible programmer. I shouldn't say that on stage with cameras running. But I can read and reason. And I really wanted to know if, given a background in building these smaller scale emulators, that I could do something bigger and Game Boys. What's a Game Boy? Asked literally nobody ever. Everyone knows what a Game Boy is. A Game Boy, more specifically, is an 8-bit handheld game console developed and manufactured by Nintendo. The first handheld in the Game Boy family. It was first released in Japan on April the 21st, 1989, then North America 3 months later, and lastly in Europe a year later. It was designed by the same team that developed the Game & Watch, that's why it's a Game Boy, and several Nintendo Entertainment System games. Thank you, Wikipedia. I mean, we all know what a Game Boy is. They're like literally iconic. You can set them on fire and they still work. I have literally seen this happen. They saw off about 50 billion competitor consoles by being simple, accessible, resilient, and fun. And you know what? This is my childhood. Like, legitimately, this is deeply personal to me. It's my childhood in a little plastic mold. It's where my lifelong obsession with video games came from. I literally typoed "game" from in my notes when I was writing this. Game Boys are awesome. And personally, I grew up in Asia in the 1980s, and I remember getting a Game Boy from the Temple Street night market in Hong Kong, and I was always excited because we'd go walking down, the night market streets, and they always had these game stores with colourful boxes stacked up in the windows, and it really stuck with me. So not only is it awesome, it's personal, right? We don't care where you bought your Game Boy. I can hear you all thinking, what is a Game Boy? All right. Don't ask the same question twice, it's rude. A Game Boy has an 8-bit 4.19 megahertz CPU, 8 kilobytes of RAM, and a 160 by 144 pixel display. The CPU is similar to an older Intel 8080 CPU, and most of the assemblers for it use Z80 syntax. It's a custom chip, but the instructions are based on very, very well-known hardware. Now, I read those technical specs and I felt emboldened. I'm going to say that it's just like the Z80. It's like, well old. How hard can this possibly be? I adore games, and I always have. And I love the 90s and 2000s emulation porting scene. But a few things specifically sent me down this particular path. Now, I watched this great YouTube video on a channel called MVG, Modern Vintage Gamer. I don't know if anyone's seen it. He's a big deal on the internet. And he did a time-lapse of importing the game Another World to the original Xbox, which I thought, that was pretty cool. And I'd spent some time the past couple of years transliterating software for clients. So I'd been porting Python and Java things into .NET and .NET Core, and ironically porting .NET Core and C# stuff into TypeScript and JavaScript. So I felt quite confident transliterating code, and I've been working on some C and C++ hardware projects around building kind of displays and stuff as well. And I thought, hey, Z80 processor isn't too different from Chip 8 in complexity. Absolutely not true. I wonder if I can write a lo-fi Game Boy emulator that could be used to like capture frames and send it to some kind of hardware. That'd be really cool. So I fell down this black hole of 1990s era PDFs about reverse engineering the Game Boy hardware. And you know those like Wikipedia holes that you fall into sometimes? This is like really deep. Really, really deep. Like the 90s were wild. So I spent about a day reading this thing called PansDocs, which is a 25-year-long community effort to catalog all the details of Game Boy hardware. Like, this is like peak 1990s era deep technical unpacking and reverse engineering of Game Boy hardware. It's like a headful, really, really, really is. They're wonderful documentation. I would not recommend them as a casual bedtime read. No plot, the characters are boring. So I skipped to what I felt was the most interesting place to start, looking to like read some information from cartridges. I opened Visual Studio and I started to code. So, while from the frame of reference of writing an entire emulator, parsing a cartridge might not seem like that much of a big deal, I got it done pretty quickly, like we're talking a couple of hours. So I grabbed my copy of totally legally backed up Nintendo, please, please don't sue me, I swear, Super Mario Land, which I happen to have on my computer as a ROM. And actually, I still actually have my copy of Super Mario Land that I got when I was a kid, so this is probably actually the most legal thing I've ever done. And I managed to parse the boot logo, the cartridge information, and the metadata within a few hours of hacking around. You literally parse the byte stream from the top of the ROM. Kind of interesting. And it felt real and exciting, like I had some virtual memory. I had a class called CPU, and I had some opcodes, and it was starting to tick. Super, super cool. And then I got stuck. Like, really, really, really stuck. I felt like I had a reasonable grasp of the Game Boy hardware, but I couldn't understand why some of my opcodes, or what they were meant to do. I was reading the docs, and I couldn't work out what they were doing. And my emulator kept on crashing in the boot sequence. Now, to make matters even more confusing, the documentation had started to use notation that I didn't understand. Now, I'm not sure if it's some fairly standard high school maths thing, but I am not a maths person. And it was really boiling my brain. I didn't understand the notation. I was trying to implement the opcodes for the Game Boy CPU, just like in the earlier Chip 8 example, as a glorified switch statement, and I just kept getting lost. Now, not to be deterred, I went hunting for some other code bases that had been here before in an attempt to find something that could at least help me understand the notation in the documentation. Now, I found a couple of emulators that worked in a couple of different languages, and I stumbled across the Coffee GB project. And it was a working emulator in Java 1.8. No, I jest. It was wonderful, literally wonderful. A clonable repository that would build when I checked it out, that I could reason about in a language I understood. Like, how often do you find that in open source projects? All my Christmases at once. So what I figured is I could try transliterating this MIT licensed code base and use some of the open source test suites that were in that code base to kind of glue things together at the end and work out what I was getting wrong. So, because we all like to shave yaks, I started off by losing an entire day converting Coffee GB to Kotlin, because I thought, oh, Kotlin would be closer to C# and it'd be easier to understand. Like, it worked. Like, I do have a weird nascent port of it in Kotlin, but there's no point in that thing existing. So before deciding to commit, and I did a like-for-like transliteration of the whole Java source code across into NetCore 3.1 in an attempt to hopefully understand where my own opcode processing was going wrong. Yeah, I keep on saying transliterate. Let's talk about that really, really specifically. This is originally a language term, meaning very, very specifically to write or print a letter or word using the closest corresponding letters of a different alphabet or script. So for a little clarification, a transliteration, as opposed to just a port, is a line-for-line cosmetic-only change. Now, you change the absolute minimum code required to get the software compiling in the target environment, and then do subsequent second and third passes to port things that are missing or don't really convert like for like. So, porting and transliterating software is a very, very specific discipline, which is counter to how I and probably all of you would build software normally. There are these three passes. So, firstly, you transliterate it until it compiles. So you start at the entry point and you work your way down. Now, this normally involves starting at the main method and only migrating code that gets called file by file. And then secondly, you port over any test suite once the transliteration is done and ensure that the tests match the original. Once you're in that place of safely, you convert the code to be idiomatic in the target language. And you have to be really disciplined about sticking to those exact three phases to make sure you don't introduce errors. Now, in the above examples, you can see how the Java is subtly changed into C#, with package declarations swapped for namespaces and attributes being removed. Now, later, much of that syntax is converted to C#8, so we're using expression-bodied methods that obviously don't exist in Java. And then, this is a fairly trite and succinct example just to fit on some slides, but some other conversions are far more dramatic, in fact. So you might think this is a set of obvious steps, but you end up doing some really, really unnatural things to the code base that often totally go against your instincts. Now, during the first phase especially, you often find yourself fighting your tools because you're at a disadvantage if you diverge in any way from the original source code to prevent comparisons. Now, this means you have to do horrible things like keep the naming conventions and casings and odd non-idiomatic qualities of the foreign code base, right? Precisely as they are until you're at a point of safety. Now, you also have to get very, very comfortable with throwing not implemented exceptions like literally everywhere. So, especially where a direct equivalent is not available and you've managed to get the code until you've managed to get the code executing. Now, the sooner you get to a place where you can start transliterating the available tests, the better. because you'll know early on if you're going off track, right? So you kind of want to get compiling, you want to get tests compiling, and you want them all failing, and then you can chip away and chip away. So ideally, to do this, you need a good reading grasp of the source language and like a relatively advanced grasp of the target language that you're porting to in an attempt to convert some of the more subtle differences. So in this particular code base, for example, Java has really rich enums, which often have behavior loaded into them, which we totally don't have in C#, right? In C#, they're just integers. Now, producing similar syntactic constructs that could be used in the same way is quite important. So you kind of require a reasonable mastery of the target language to pull that off without getting yourself stuck with a non-compiling code base. So you have to do things like when you're porting enums, build extension methods on the enum values that you can call to replicate that kind of Java-like behavior and APIs. So once I'd found my groove transliterating the CoffeeGB code base, a couple of things became apparent. So firstly, the UI was just never going to port. Absolutely wasn't going to port, not trivially. It was a bunch of Java JWT code, and I don't know if anyone else remembers the 1990s, but that's where I think the last person that thought about JWT code still is. There was no point in trying to convert that like for like. I wasn't going to port Java windowing toolkit to C#. Like, there's the shaving yaks and like importing your own herd of yaks to shave one by one. The JWT code, however, slightly annoyingly, was responsible for both drawing the game to the screen and handling controller inputs in the source emulator. Fine, write it down, another thing to do. So my first target quickly became to get the headless mode in the original code base booting a Game Boy cartridge. Now, headless mode was designed to run the emulator without visual output controls in a console window. I figured if I could do enough to just get that running, I could port the unit tests that exercise some of the community-authored homebrew ROMs. And there's a set of ROMs that are designed to test various aspects of the Game Boy hardware to make sure your emulators are working correctly. So I deleted all the JWT code. I left all the stubs of the code paths and the function calls in place, just replacing their bodies with not implemented exceptions. And I implemented a few interfaces with empty implementations, and I managed to cajole headless mode into life. So you can see the code for headless mode as it still exists today in the source code here. You know, I'm passing in null displays and null controllers and null sound and null inputs, along with, amusingly, the remnants of some of the JWT code left commented out for reference in case I needed to look up what it did. And you know what? Like, I cannot state enough how well compartmentalized the original code base was. Like, honestly. Properly kudos to the original author. I was very, very lucky that when it came to writing a new display, the original code kept an array of pixel colors packed into an integer, and the various graphics opcodes produced those, and it actually resulted in this pixel array. So all I really had to do to get stuff on screen was convert that array of packed integers into X, Y coordinates and find a way to like quickly get it on the screen, right? So I extracted these RGB values, and I raised a C# event every time they changed. And I created this new bitmap display class. So to match the original implementation, my display class runs on its own thread, refreshing distinctly from the CPU. So I've kind of got my CPU ticking and emitting events, and then a bitmap display class listening to them and needing to do something, right? I just need something to draw some pixels. Anyone done any desktop programming in .NET recently and knows how diverse the and possibly not well maintained the set of things are? Well, you know what? I nailed it. WinForms. I'm not even joking. You heard me right. I ported a Game Boy emulator to .NET Core 3.1 just to run it in a WinForms UI, and I'm not sorry, and I'd do it again. The number of questions I got about this, my sanity, why I wasn't running WPF, if anyone still used WinForms, if WinForms ran on .NET Core, was quite excellent. People forget that WinForms was designed to be easy to use for rapid application development, and it kind of lets you get stuff on the screen really, really quickly, and computers are fast now, so it's fine. WinForms is actually secretly kind of awesome, and it does run on .NET Core now, 5 and 6, only on Windows, obviously, because WinForms on the Mac doesn't make any sense, and it just works. So about 200 lines of code later, I had a WinForms UI with a picture box on it that I could update every time my Game Boy emulator raised an event. And if you're eagle-eyed and look closely at the background images here, you'll notice another nice thing that came free from WinForms. Input handling, just like the original JWT codebase. So I could hook an implementation of a controller class up to the WinForms window key press events, and it just worked. Like, I think I hacked this together in about 45 minutes, and I sat there thinking that everyone was going to judge me incredibly harshly, but I was unrepentant. and it worked. Like, legit, it worked, kind of. Kind of. So once I got to this point where I had the title screen of Mario booting in C# and side by side the original Java code base booting the same game, I realized that I'd made some kind of terrible error where every time I pressed start, the game would crash. And yeah, obviously enough of my port was working. Like, I'd got somewhere, I had a screen on. But establishing where my code had diverged from the original definitely working code base was a terrifying prospect. But luckily, I am not the first person to ever try and write a Game Boy emulator, right? So we go back to the internet in the face of our own failures. So there's a really good set of homebrew test ROMs that exercise the Game Boy hardware that I mentioned earlier. Now, what I wanted to do is I wanted to run the test ROMs in both emulators side by side and see where they diverged. They're wonderfully named. One of them is called Blarg, and the other is the Moon Eye test ROMs. I think the latter is actually from a work-in-progress Rust emulator. I don't know where people make up these names. Fine. So I ported the test harness across to the original code base, and I got the test ROMs running. And just as I suspected, tests that were passing in the Java code base were failing in my port. This was a great first step, really. I had failing tests, and I hope everyone understands the value of a failing test when something isn't working. I just needed to find out what exactly I'd broken. And, I'd ported, 5,000 lines of code. Now, these are both low-level emulators at this point, and it's important to understand this. So they literally implement the opcodes of the hardware, and they tick at the clock rate of the CPU, so 4.19 megahertz. Doesn't sound like a lot of megahertz until it's a loop. Like thousands and thousands and thousands of iterations of CPU ticks a second. Now, you can't meaningfully step through the code because the number of operations that have to complete to see any change in memory is like a lot. Thousands and thousands of steps. But that's okay. We live in Visual Studio, right? We have tools that are good. We have things like conditional breakpoints. I felt emboldened. I can just put a conditional breakpoint in this thing, and when a value changes that I don't expect in memory, cool, break into a debugger. So ironically, the performance overhead of applying a conditional breakpoint to one of my virtual CPU registers was so severe that I couldn't even get Visual Studio to process a single test case as far as the first error in like less than 10 minutes on like a Ryzen 5950X, right? It literally couldn't run fast enough with that instrumentation in place. So I knew that I had to get both code bases into a point where I had a breakpoint where memory state diverged, right? That was the goal. And I could solve the problem I was seeing if I could do that. I just wasn't really immediately sure how. So you may all recognize this from your regular jobs as your integration tests being your only tests, right? It's always a bad place when your integration tests are your only tests because you know something is broken, just not where. So I ended up spending a morning building two tools. I started by building a debugging tool, and I built a client in both Java and C# that keeps the ticks of the emulators in sync, breaking them both into the debugger when their memory state diffed through doing like a hash of the memory. Both emulators would call a HTTP server with a hash of their current memory state, and where it differed, it would make them pause, right? It seems like you can see where this is going, right? Which is a great idea in theory, but I just mentioned that conditional breakpoints were slow. Yeah, not very smart sometimes. It worked, but I didn't get there with it because it was so slow, right? There was way too much overhead. Like, it helped me find like one bug, which was cool, and I fixed it, and it did kind of pay off for the sake of a morning's effort. But too much overhead, so I had to go lo-fi. I built a logging function into each emulator that I could wrap around the test cases that just dumps the memory state to a massive text file on every CPU tick, right? So I left it running for half an hour, right? And I knew that when the test passed in the first emulator, the one in the other one should have passed, and I could stop it. Old tricks are the best tricks. And so what happened is I did these lengthy diffs on like multi-gigabyte long log files. We're talking 10, 20 gig long log files for like 20 seconds of execution to find the tick number where the emulators diverged. And it worked. So once I had a tick number, I just added a debugger break into the code wrapped in an if statement. If tick is 29,000 whatever, debugger break. Perfect. And well, I added the immediate tick before, so I could then step through execution. And it was important that I kept those two transliterated code bases so close, because actually, when the test cases passed or failed equally, I could pretty much look at the same line number of code and just step through side by side. If I diverged them by this point, debugging would have been a nightmare, and honestly, I would have probably given up. So the first bug that I fixed this way felt a little bit like magic. Like, I felt like I'd pulled off the heist of the century, like, just this sense of accomplishment of, like, did you actually just build your own debugging tools and it worked? Yes, go me. It took about a day of doing this, but I got my emulator in parity with the original CoffeeGB source, and I could start refactoring it at that point, like it was in a good place. So what was the crashing bug, for the sake of argument? So I'd fallen foul of converting one of the Java data structures to C#. Now, as I mentioned earlier, in Java, enums can have methods. And I'd hastily transliterated some code that categorized enums for different banks of memory in the Game Boy. Now, you'll notice if you glance to the top right here that the enum names are used to categorize different parts of the same type of memory. So, for instance, and it's a little bit fuzzy, so ROM underscore MBC3 and ROM underscore MBC3 RAM are both identifying parts of the memory that make up MBC3. So that stands for Memory Bank Controller 3. It's part of the Game Boy cartridge physically. So the way that Game Boy cartridges work is they have memory banks to expand the amount of memory available to games, which gets switched out dynamically by some opcodes. That's why, just coincidentally, that in the 90s, when they advertised Game Boy games, the sizes of cartridges were used in marketing material. Like, oh, it's a 4 megabyte cartridge. Right, and it's because they use that memory basically for graphics all the time. It was just for storing sprite data. So the bigger the megs, the more graphics, the nicer the game tended to look. And it was because they had more expensive multiple memory banks they were switching out. So the code in the emulator that implemented the opcode to switch these memory banks needed to check if the current memory bank location was part of one of these memory banks. Now, the original Java implementation used a regular expression to check the name of the enum member. So it basically checked if it just contained the name of the memory bank it was looking for. Now, I had hastily replaced that regular expression with a string contains call that presumed that the enum member would always have an underscore, followed by MBC something, followed by an underscore, which works perfectly well for the string ROM underscore MBC3 underscore RAM, 2 underscores, but not so well for ROM underscore MBC3. Oops. Oops. We are all fallible. So while trying to switch memory banks, my code was just failing, and quickly replacing that string contains method with the original regular expression just fixed the bug, right? You know, I know there are way more idiomatic C# ways to do this, like you can mark them up with attributes or God knows what. But it worked, honestly, fine. Like, don't sweat the small stuff, right? So one of the final entertaining surprises was the afternoon I lost trying to find out why my emulator was slow. So on a related note, you'd be surprised what a difference that release builds make. It's like a list of basic C# mistakes. Yeah, I spent what felt like an eternity trying to profile the performance of the emulator because I just couldn't work out why it was performing so slow and so badly. And it was just because it was being observed. Oops. So the program was just ticking so fast that the overhead of collecting metrics and debugging instrumentation just slowed the program down. So simply compiling and running in release mode without a debugger attached totally matched the performance of the original emulator, which was also running in a release build without a debugger attached, right? Totally fine. I've also perhaps skirted around the issue of audio in the emulator because there is no audio. I've not written it because I don't know how. I've never done audio programming before, and I'm looking into various audio wrappers. I know there's like N-Audio, and I'll try and work out how to make Tetris sing. It's just a slow process learning things you really don't know. And it worked, you know. Throughout the first couple of weeks of this project, and given we were all in quarantine at the time this was happening, right? This is a peak lockdown, stop me going insane project. I've been teasing the internet with screenshots of Game Boy games and things like that. So once I got to the point where the UI wasn't crashing and the code was suitably ported, I just chucked the emulator on GitHub, you know, mostly for the fun of it. And generally, people have enjoyed seeing this kind of project done in C# rather than yet another business application. There's an acronym that's going around at the moment, like a blobum or something, like a boring line of business application. I just wanted something that wasn't that. And yeah, I stuck a ridiculous ASCII art renderer on the front of it so you can play Super Mario and ASCII art on the command line. It's everyone's bucket list item, right? Totally. Why would you not want that? And really, that was the reason for doing this at all, and that's kind of the point I really want to make. You know, C# is a language I love and I feel very comfortable with. I love the direction that .NET Core 5.6 Plus is going, and I'm on a bit of a journey at the moment trying to prove that we're really at a place with .NET where it can really do anything any other runtime or language can do, at least as performantly and often plenty more beautifully in code, right? Like I truly believe that. And it's wonderful to see other people like engaging with it in good faith and you know, seeing the same thing. You know, interestingly, after I put this online, I got a message from a guy who used it for like a Twitter Plays Pokemon thing, where he used the back end for this to update his user picture, and people could tweet controls at him, and they played their way through Pokemon. Yeah, it was awesome, right? Though needless to say, it wasn't without its distractors. So, you know, everyone always says, never read the comments. Should we read some of the comments together? It's going to be good. I always like to engage. And there was one comment that both stuck with me and I thought was important enough to highlight. So let's make a stranger from Reddit famous for a moment. Ooh, oh God. Code quality is questionable. Here's how the author omits frames. They create a new image. Big fat allocation. That'd be like, I don't know, my hip-hop name. Iterate over every pixel, convert its value to a string, and immediately pass it back as a source for an RGB color and fill a single pixel with it. Create a memory stream with oh God, he just kind of went big fat allocation, another big fat allocation. Call to just look at this crap, right? Some electron-level resource wasting, he probably says, while Visual Studio Code and Slack are open on his desktop. Oh, Jesus Christ. Reddit, as ever, is a mixed bag. So I had a bunch of really interesting conversations with people in the .NET and C# subreddits. The general programming subreddits, on the other hand, not so much. It's easy to forget how hostile people can be to absolutely nothing at all. And legitimately, one of the takeaways of this process for me was this. As programmers, we can be short, we can be snipey, we can dig through code contextless and take swipes at things just to bring each other down, right? Everything in that comment, 100% true. I could totally be better. But you know what? The program consumes between 30 and 50 megabytes of RAM in total. I benchmarked it. And I'd do it all again in a heartbeat to put out something cool and interesting in the world that people got a little bit of joy from. Loud and clear, no gatekeepers, no perfection, doesn't exist. Do the fun thing. Enjoy yourselves, share stuff, otherwise bores like that win. Right? And absolutely, I don't want to live in a world with those people. Like, my God. Luckily, the bores never win in face of you doing cool stuff, honestly. So within a day or two of pushing out some tweets with links to the code, I had a couple of pull requests. One with a monogame UI that let the emulator run on various devices. One with an Avalonia UI that let the emulator run on Linux and Mac, as well as the existing WinForms UI, cross-platform headless CLI with its ASCII art. You know, like, you can reference the Game Boy emulator as a library in your programs. I don't know why you would ever do that or what use it would be, but you could do it if you want to. And, you know, the Twitter Plays Pokemon thing, you know, Scott Hanselman wrote a blog post about it where he was hacking some code in it. Like, it's fun. People like fun. Why do people hate fun? You know, I'm very happy, and you know, the lesson for me for this, and the lesson I want to leave everybody with is, you know, don't give up when you get stuck. You know, I know it sounds really, really trite, but everything we do in software is built on the shoulders of other talented people that build things before us, and it's easy to get stuck, and it's easy to give up, and it's hard to go and decide to look around for inspiration. You know, I'm super, super thankful for the wonderfully high-quality CoffeeGB code base. Like, I made a snide jab at it being Java 1.8, but it was a brilliant code base, like legitimately brilliant code base. I had the pleasure of adapting it. I had the pleasure of merging it with my own work and my own efforts. You know, I'm happy I didn't actually succumb to my own hubris and decide that if I couldn't just work it out on my own, then it wasn't worth doing. You know, I'm absolutely thrilled that by sacrificing that little bit of ego, there's something cool and fun that people can play with. And I hope, you know, I hope if you get the chance, have some fun with it. Like, trash the place. It's cool. I'm excited. You can find me on the internet in all these places. Feel free to tweet at me, harass me, buy my books. Don't Reddit me. I promise I don't bite. Thank you so much for coming. Really, thank you. There's a whole room here. Any questions? I probably can't answer them, but I'm happy to try.
How
No.
much time it took?
2.5 weeks from the first idea. I say that. I always misrepresent the amount of time. What it really was a month of me sleeping on the idea, and then a morning of waking up and going, I can probably do that, let's start. And you know what, like, we were all locked down, and I was in this place where I quit all my jobs, all my client engagements on the 1st of February 2020 to go traveling, to do some conferences. I had like a wedding booked in South Africa, I had a trip to New York, like 3 conferences. So that lasted like 3 weeks. And I needed to fill up the rest of my year, so I did like 14 weird projects in a year just to see what weird stuff I could do, because it was my own time. So yeah, it was about a month of stewing and then 2.5 weeks of hacking, head down. Excuse me. Any more? Amazing. Thank you so much. And enjoy the rest of your day. Like, thank you to the organizers. This has been a labor of love in the face of all adversity.